Hi, my name is Manuel Santos, and this is a joint work with Paulo Mateus and Chrysoula Vlachou, which you can find at this archive link. The work goes under the title of Quantum Universally Composable Oblivious Linear Evaluation, and I will walk you through this poster in this presentation. Let us start by briefly defining and explaining the importance of oblivious linear evaluation, or for short, OLE. This is a two-party protocol between Alice and Bob, and the idea is that they can jointly compute some linear function ax plus b in a way that Alice controls the function coefficients a and b, and Bob controls its input x. This primitive comes with some security requirements, because basically Bob gets no knowledge about Alice's inputs, and Alice gets no knowledge about Bob's inputs as well. So looking at the picture, Alice inputs a and b, and Bob inputs x, and the functionality outputs nothing to Alice and outputs the evaluation of f at point x to Bob. This primitive is very important because basically it allows secure computation of general functions. And by secure, it means that the parties computing the function stay oblivious about the inputs of the other parties. In classical cryptography, OLE is produced with public key cryptography, which may be prone to quantum computer attacks, so it is kind of desirable to develop protocols based on quantum information that are robust against quantum computer attacks. And up until now, there was no direct OLE protocol based on quantum information, and in this work, we proposed the first one. The proposed protocol is based on this relation one, and in fact, it is possible to build such a protocol because of a particular linear relation between the base elements. The base elements that we use, these e to the theta of r, they come from a set of mutually unbiased bases. The theta here denotes the base being used, and the r denotes the vector inside each basis. This linear relation, a theta minus b plus r, comes when we apply a specific operator, VBA, to these states. So in case Alice controls the operator, VBA, and Bob the quantum states, E theta r, they can compute a linear function, a theta minus b. So by controlling the operator, Alice controls the function, and by controlling theta and r, Bob controls the inputs of the function f. Let us briefly look at how the protocol works. So Alice inputs a and b, and Bob inputs x. And the protocol is divided into two main phases: the quantum phase and the processing phase. The first phase uses quantum communication and the relation one that we just saw in order to output a vector of linear functions a0i theta I minus b0i. To do this, Bob chooses randomly m base elements e theta I, ri, and sends them to Alice. Then Alice prepares several operators, v b0i, a0i, and applies them to the states received from Bob. Then she sends the resulting states to Bob, and now he is able to measure them and get m evaluations of linear functions defined by Alice. These intermediate steps are used to ensure that Bob behaves honestly. So Bob uses a commitment functionality to commit to his values, and Alice tests a subset T of the received states and checks the honesty of Bob. The aim of the processing phase is basically to extract one secure linear evaluation out of the vector y0, and this is done based on a family of hash functions that are given by the inner product with a random vector k. Regarding the security of the protocol, we proved its security in the universally composability framework, which renders strong security properties. In particular, it allows the protocol to be arbitrarily composed with itself, and with other protocols while preserving the overall security. So as usual in UC proofs, we analyze separately the behavior of a dishonest Alice and dishonest Bob. Also, in UC proofs, we compare two scenarios, the ideal world scenario and the real world scenario. In the real scenario, we have Alice and Bob interacting with themselves, but in the ideal scenario, there is a special entity called the simulator that interacts with the dishonest party. And in summary, we prove the protocol to be secure if we can build a simulator that, while interacting with the dishonest party is not able to distinguish the execution of the protocol with the simulator from the interaction with the real honest party. So basically, when developing a simulator, it must have two important features. This extractability feature, which basically allows the simulator to extract the inputs of the dishonest party, and this important indistinguishability feature between the real and the ideal execution. For a dishonest Alice, the simulator extracts her inputs using an entanglement attack that characterizes the operator's VBA. The indistinguishability comes from the fact that the simulator has the power to reprogram the commitment functionality in a way that prevents the adversary to distinguish the real Bob from the simulator. Regarding dishonest Bob, the extractability also comes from the control that the simulator has over the commitment functionality. And the indistinguishability between the real and ideal execution comes from two elements. First, we have that Bob has a limited amount of knowledge about the vectors A0 and A in the protocol. And this is mainly because of the initial checking phase with the commitment functionality. Secondly, there is a privacy amplification step where any knowledge Bob may have from vectors A0 and A is erased by this inner product operation. So these two elements together renders the indistinguishability feature required for the UC proof. Finally, we present two useful generalizations of the quantum Ole protocol. The first one is that we can generalize the relation 1 that holds for Hilbert spaces with prime dimension. We can generalize it to Galois fields with prime power dimensions. So if we adapt the operations in the protocol, we have a secure protocol in Galois fields. The other generalization is basically the ability to adapt the quantum Ole protocol to a vectorized version called vector Ole. And in this version, basically Alice inputs two vectors, A and B, and Bob only one single element, X. Then Bob receives a vector that corresponds to the evaluation of several linear functions at just one point, X. In order to achieve this, we just need to slightly change the quantum Ole protocol. And the main idea is that we can extract several linear evaluations out of these Y0 vectors instead of just one. And this is achieved by generating several vectors K in some specific way instead of just one. Thank you very much.